math and beats. We are here to start the conversation about calculus topics. And in order to start that initial conversation, I think we need a little motivational type of section. So this little discussion we're about to have is that motivational topic. And we are going to talk about the differences between what is an average velocity versus what is an instantaneous velocity. Let's get going here. First of all, I just want to quickly refresh some ideas. A rate, what is a rate? It is a ratio of two quantities which have two different units. For example, 45 miles per hour is an example of a rate, as it is a ratio of 45 miles per 1 hour, different units, ratio, we get a rate, 45 miles per hour. Now, in particular, we're interested in the average rate of change. Remember that the average rate of change of some function over some interval, say from A to B inclusive, is the value of the ratio right here, f of b minus f of a, the change in the output values, divided by b minus a, the change in the input values. Sometimes we denote that by AROC for average rate of change of the function f subscript over the interval right below there, a to b. So we're interested in this because it has to do with average velocity, as we'll see. Now, if you look at the graph down here, well, look at that blue graph. That's the graph of f of x. And what we see is a line connecting the points a, f of a and b, f of b. That line has a slope associated with it. In fact, remember, slope is defined to be the change in the output over the change of the input over that particular interval. So in fact, the average rate of change of this function that we see in this particular situation, f over the interval a to b, is actually, as we said, f of b minus f of a, changing the output over b minus a. That ends up just being the same thing as the slope of this line connecting the 2 points a, f of a and b, f of b. So this red line we see right here, that thing has slope equal to the average rate of change of the function over the particular interval. So it's actually the same thing. So that's all said right down here. Average rate of change of the function over an interval defined to be f of b minus f of a over b minus a, which is really the change in the output, a change in y, over the change in the input, a change of x, over the interval a to b, is the same as the slope of the secant line. So remember, the secant line is just the line that we're talking about in the figure here. It's a line connecting two distinct points on the curve of some function. And in this case, those 2 points being a, f of a and b, f of b. Now, what does it tell us? It tells us, on average, how much the function has changed over the interval from a to b. Has it gone up? Has it gone down on average? And if so, per unit of increase in the horizontal direction, how much have we gone up or down per unit of the vertical direction? So that is, on average, for every b minus a units in the horizontal direction, right? How much has the function changed, f of b minus f of a, right, in the vertical direction? Might go up, might go down. And so on average, how much did we go up or down by per unit in the input direction? So I'm just trying to refresh your memory here about some of this stuff. And note that units are important. So if the outputs y have units a and the inputs x have units b, then the average rate of change, which is the ratio of the outputs over the inputs over that interval, will have units a over b. So we need to keep that in mind. It'll always be true. What those units are all dependent upon the context of the situation. So we are particularly interested in calculating what's called the average velocity, which is the average rate of change. Okay, now recall that if we have some function, say s of t, and this function gives the position of an object s being the output here, say units of feet, based on how many seconds, let's say, could be other time units too, but in this case, seconds, t that have passed. So you got the position of an object relative to some location, and after so much time has gone by, seconds here, we can tell you, the position of this object relative to some location. So you got a function that does this, measuring the position of some object. Then we say that the average velocity of the object over that interval of time, a to b, is given by the definition above. We say the average velocity, VEL, for instance, is just a type of notation of the position function s over the interval a to b, is the ratio of the outputs over the inputs over that interval of time. So here would be the change in the output, s of b minus s of a in feet, and then the change in time, b minus a seconds. So it tells us this rate. On average, not only how fast were we moving over this particular interval of time, but in what direction as well, because this could be negative or positive, and depending on what it is, it really tells us whether or not we're going up or down in position over that particular interval on average. Let's look at an example here to get an idea. Got some mischievous teenager here. They throw the ball from the top of a building upwards into the air, and it's known that the initial upward velocity of the ball is 16 feet per second, and this is done from a height of 32 feet above the ground level. Then we can say that the position of the ball, let's say s measured in feet, relative to the ground level, t seconds after it has been thrown, is modeled by this position function here. S of t equals negative 16t squared plus 16t plus 32. This person's going to throw the ball up from the top of a building. It's going to go up and it's going to come down, assuming we're on planet Earth, of course. What we'd like to do is just determine the average velocity of the ball from t equals a half second to t equals 1 second. So let's just go ahead and do that and think about what's going on. The average velocity of this ball over the interval of time, half second to 1 second, is, by definition, s of 1 minus s of 0.5 over 1 minus 0.5. S of 1, plug it in, that's negative 16 times 1 squared plus 16 times 1 plus a 32. There's our s of 1 minus the quantity s of 0.5 or s of half is negative 16 times 0.5 squared plus 16 times 0.5 plus 32. Minus all that. And then on the bottom, of course, change in time is just half a second, 0.5 seconds. Now, if you do the calculations, it ends up that s of 0.5 is equal to 36 and s of 1 is equal to 32. So you plug it in. This is 32 minus 36 over 0.5. That's negative 4 divided by a half, which is negative 8. Now, keeping in mind here the whole time, we have units associated with this, right? The units in the output change is units of feet, and the units of the input change is units of second. So this is negative 8 feet per second. That's the average velocity of the ball over this time interval. And because it's negative, remember this is the slope of the secant line connecting the points half comma s of half and 1 comma s of 1 on the graph of the function. It's the slope of that line. Then what it tells us on average that per second that goes by, the ball will have decreased in position by 8 feet per second since it's negative, right? Negative slopes correspond to lines that are decreasing. Positive slopes are corresponding to lines that are increasing. So on average, this was what's happening over this 1/2 second interval of time. The graph right below here is depicting everything I just talked about. And as you can see, we got the line. I'm going to call it L sub S here, that red line, that secant line connecting the points Q and P, Q being 0.5 S of 0.5 and point P being 1 comma S of 1. So I find the slope of that line over this interval of time. And that line right there has slope equal to -8. So it's telling us on average per unit time here, per second, how much has the ball's position gone up or down over the interval on time on average. Now remember, the title of this section here that we're talking about, this video, is comparing what we just talked about, the average velocity, right? How fast has something gone up or down over some interval of time on average versus what's called the instantaneous velocity. The instantaneous velocity of an object, say, whose position function is given by s of t, is this function, which we're going to denote by this here. So that's pronounced s prime of t. So that little dash there is the prime. Talk way more about what that means later in these calculus discussions. But in general, the instantaneous velocity of some object at time t, denoted by s prime of t, tells us how fast the object is moving at an instant in time, and also in what direction. So instead, what we were talking about before was over some time interval, how much has the function gone up or down? How much has the object done that over some particular interval on average, right, per unit of time? Now instead, you think of the average rate of change, the average velocity of the object over some interval of time. You kind of see it happen, right? The person throws the ball and then you watch it go through the air after a second or two or whatever. But now instead, you take a picture at some instant. Click, click. Take the picture. At that instant, you take that picture. How fast was the ball moving? How fast was the object moving? And in what direction was it moving? That's what this idea about instantaneous velocity is about, and is a really big underlying motivational idea behind a lot of the mathematics we do in calculus. So click, click, taking a picture at an instant versus on average over an interval, what's going on. Let's look at another example here, this last one of this discussion. Let's assume that we got the same thing as before. The teenager was throwing the ball off the top of the roof upwards, and then it comes down. So we still got the same position function here. S of t is negative 16t squared plus 16t plus 32. And we'd like to figure out what the instantaneous velocity of the ball is at 1 second. Disregard the W. So after 1 second has passed, someone takes a picture of the ball. How fast was it moving, and in what direction would it be moving? To do this, we're going to set up a situation. Let's let Q be any point on S. Okay, so let's just say it's A, comma, S of A, just for instance. Okay, it's kind of tripping there for a second. Okay, so it's just any arbitrary point on the graph of the function, anywhere. And let's let point P be the point that we're interested in, 1 comma s of 1, remembering that s of 1 was equal to 32. So this is 1 comma 32. Okay. So we got the point P, it's fixed, this point of interest. We got the point Q, any point on S. Then we could discuss, for any point on S, what the average velocity is between point Q and P. It follows that the average velocity of the ball between P and Q is, well, just compute it. It's going to be change in the output, S of 1 minus S of A, and the change of the input, 1 minus A, right? Remembering the units feet per second here. Well, we could compute that. S of 1 was 32, and then minus the quantity S of A would be negative 16A squared, plus a 16A, plus a 32, all over 1 minus A, again, feet per second. And if we just cancel a couple things out here, what we get is a 16A squared minus 16A over 1 minus A. So that's going to be the slope. Excuse me. That's going to be the, I was getting ahead of myself. That's going to be the average rate of change, the average velocity, which is the slope of the secant line connecting the points 1 comma S of 1 to A comma S of A. And as A changes, this slope of the secant line should change. Let's go ahead and take a look at a little picture here. Okay, so what we see in this picture is exactly the situation. Now, right now, we're at the point for Q, which is a half comma S of a half, which is what we were looking at earlier. And then if you connect that line to the point P, 1 comma S of 1 on the graph of S, then the slope of that secant line connecting the 2 points, which is the average velocity of the ball over this half-second interval, was negative 8 feet per second, if you recall, right? Now, what we're saying now is Q can be any point. So if I move it to the left a little bit, right, the line is getting less steep, and correspondingly, the magnitude of my slope is getting smaller. And if I move it this way, right, it gets a little steeper, the slope becomes steeper, but still negative. And so that's what we're saying, is we're going to consider any of these average velocities as the point P stays fixed at t equals 1 second, and as Q moves around. Now let's think a little more. If I start moving Q really, really close to P, right, correspondingly, my t value down here is getting closer and closer to 1. We still have this line, the secant line connecting Q and P, and over here we're calculating that slope based on the formula that we saw a moment ago. And eventually, if I get really, really, really close, right, then that line that we see, that secant line connecting the 2 points, well, it's so tiny, right? The length of it is getting smaller because the time interval down here is also getting really small, right? Now, when you take the picture of the ball at 1 second, click, click, how fast was it moving? You can kind of think of that in a way as there is no time interval. And so if we let it get arbitrarily close as possible, right, and we look at those slopes, then eventually the point Q becomes arbitrarily close to the point P. The time values down here get arbitrarily close to at 1 second. And it forms this idea of what we call a tangent line. And that tangent line is no longer a secant line because the 2 points are really at the same spot or getting arbitrarily close to the same spot. This is a line that just grazes the graph. Just barely touches it at that one point that we're interested in. And this is really the idea behind instantaneous velocity. We let the time interval get tinier and tinier, and let the other point forming the secant line get closer and closer to the point that we're interested in, and we look at the values of the slopes of the secant lines as they get closer and closer to the value of the slope of the tangent line. In this case, again, I'll move back a little. As we move it closer and closer and closer, it sure seems that it's getting very, very close to the slope of negative 16. So you go back over here. From that diagram, seems like this instantaneous velocity at t equals 1 second is negative 16 feet per second. So at that instant, how fast was the ball moving? It was moving at a velocity of 16 feet per second in the downwards direction, right? It was decreasing, it was going back to the ground. Now, the way that we describe this mathematically is we need something which is called limits. And so that's the whole setup here. We want to get into a conversation about limits. And so we could write things like, well, as the values of t's, the inputs, get really, really close to 1 here, right? Because they were. Then the average velocities, the slopes of those secant lines, which was s of 1's minus s of a's over 1 minus a's, seem to approach negative 16. Right? This is really the idea behind a limit. Let your input value get really, really close to a location, and then some other stuff is getting close to some other stuff. Maybe something happens or something else happens. In this case, the other stuff we're interested in is the slope of those secant lines, which represents the average velocities. And as we make the time interval tinier and tinier, as the t's get closer to the 1's, these average slopes approach what's called the instantaneous velocity, which is, in this case, approaching negative 16 feet per second. What we'd like to write moving forward is things like this. Limit as t goes to 1 of s of 1 minus s of a over 1 minus a equals negative 16. So this is the idea of a limit. We need what's called limits. And the whole conversation about what limits are, how to go about figuring them out, all that stuff, that's in the future conversations. So this was supposed to be a conversation right now about why we would even consider such a thing, right? And hopefully this gave us some motivation about to go and investigate limits further. Eventually, we're going to come back to this slope conversation. And we need limits to do that. So that's it for this first video on discussing instantaneous velocity and average velocity. Stay tuned for more videos, moving forward limits, and more stuff after that. So that's it. I'm out. And until next time, peace.